Yeah, we're going to talk about how to calculate the determinant of a matrix. This is a linear algebra operation that has a very specific definition. It's useful in calculating the solution to linear systems of linear equations. So it turns out that there's usually two ways to do this. For a 2 by 2 matrix, you can calculate the determinant directly. So we'll start off with that. We'll start off with a uh, vertical line instead of a bracket or a parenthesis means that you're calculating the determinant of this matrix. So let's take a simple 2 by 2 matrix, 1, 2, 3, 4. The definition of the determinant is that you're multiplying down and to the right. So I would take 1 times 4 minus the quantity that's down and to the left, 2 times 3. So in this case, I would have 4 minus 6 or negative 2 as the determinant of this matrix. If we want to see that in general, we can rewrite this as arbitrary terms, A11, A12, A21, A22, where they're representing row and column with the subscript. This is going to be A11 times A22 minus A12 times A21. This is the determinant of a 2 by 2 matrix. So if this was labeled the matrix A is this matrix, then the determinant of A, you would write it like that. The determinant of A is equal to this. I shouldn't really say that the matrix is equal to that. The matrix would equal this with these things being brackets instead of square lines, straight lines. Okay, so in more general, though, we can write the determinant for a arbitrarily large matrix. The way that works is that we use a method called Cramer's rule, or the method of cofactor expansion, which is going to allow us to calculate the determinant of a matrix based off of taking a larger matrix and splitting it into smaller matrices. So if I have a matrix something like 1, 2, 3, 4, 5, 6, 7, 8, 9, I have the 3 by 3 matrix. I can't use the rule of down and to the right because I don't just have down to the right and down to the left. I have this combination of things. So what I do is I look at this as a row. So I'm going to use the row 1. You can use any row, and you're going to take the cofactors, or sometimes I call them the pivot point. I'm going to take the first one. If I use that as my cofactor, I can think of that as being eliminating this column and this row. As a result, I'm left behind with this submatrix. And so I can take the determinant of this as 1 times the determinant of the 5, 6, 8, 9 remaining matrix. Minus, and we'll talk about why the minus comes in. And now I just go across the row. I do the same thing with the 2, and so I would take 2, and that would eliminate the middle column and the top row, which should leave me with the 4, the 6, the 7, and the 9. So this would be minus 2 times the 4, 6, 7, 9 determinant of that submatrix. And then I would go back to plus 3 times, now I'm eliminating the final column, so I have 4, 5, 7, 8. And that is my determinant. Now I can calculate those determinants by using the rule from the 2 by 2 matrix. So this would be 1 times 5 times 9 minus 6 times 8 minus 2 times 4 times 9 minus 6 times 7 plus 3 times 4 times 8 minus 5 times 7. Now, why is this second term minus? It turns out they alternate. They alternate in sign. They start off with a positive, then a negative, then a positive, then a negative, then a positive, then a negative. So depending on how large your matrix is, just remember that the signs of the cofactors alternate. So now I can do the arithmetic here and calculate these individual values. So I'm going to do that. So there's our arithmetic done. So I would get minus 3 plus 12 minus 9. So the determinant of that matrix is 0. Now, the same technique works for larger matrices, same idea, but the submatrices are not going to be 2 by 2s. They're going to be 3 by 3s or 4 by 4s, depending on how large of a matrix you begin with. So you can see that your expansion will be recursive. Let me demonstrate that here with a larger. We'll do a 4 by 4. 1, 2, 3, 4. Now, of course, matrices can have more numbers than just incrementally larger numbers. These are just examples to help see where we're working. So this is going to be by the cofactor expansion method. I pick my first cofactor, so I'm going to once again go across my row. Cofactor expansion can work with any row or any column. Doesn't matter which one, you just pick one and do the expansion. So in this case, I'm going to do 1 times the remaining matrix, which in this case is this 3 by 3 now, instead of a 2 by 2. So I now have the 6, 7, 8, 10, 11, 12, and 14, 15, 16 submatrix. And then I'm going to go to the next term, minus 2 times, I'm going to get a 3 by 3 matrix out of pivoting around this 2. So I'm going to use first column, third column, fourth column, etc. So this should be the row, the 5, 7, 8, 9, 11, 12, and 13, 15, 16 expansion. So then I'm going to get a plus 3 times the next 3 by 3 and plus or minus 4 times the remaining 3 by 3. I'll let you figure out what those individual matrices are going to be. But you'll see then that I'm now left with a new stage. I'm now left with 1 times the expansion of this determinant. So I can now do 1 times the determinant of this thing, which is going to be the same expansion. So I'm going to use that one. So I'm going to do 6 times 11, 12, 15, 16 minus 7 times 10, 12, 14, 16 plus 8 times 10, 11, 14, 15. And I should be careful not to put square brackets around here because that means matrix and not determinant. So I'm going to go ahead and erase those and make those into actually vertical lines because they need to represent the determinant of. Now, I can do those determinants. I can get the answer. So the whole thing now becomes an answer. So this should now fall back to become the answer of this, which would fall back as 1 times whatever that number is. So once I do that for each of these 3 by 3 matrices, the whole thing should fall back to be the answer of the original. So you can see how this is recursive. I keep calling determinant of smaller matrices. So from a computer implementation, if I have implemented the function determinant of, and I pass it the original, let's say that this original matrix is named A. If I call that as determinant of A, what that's going to do is it's going to use those cofactors in the first row and it's going to multiply it by the determinant of a smaller matrix. So this is going to be equal to the value A11 times the determinant of the submatrix. So this might be the matrix. So if this was matrix B1 and B2 and B3 and B4, you'll see that this would become the determinant of B1. That's a whole new call to the exact same function. That function would now calculate the determinant of B1 by doing the cofactors times the submatrix. And since there's finally a point where we can just write down the answer for the determinant of a 2 by 2, this recursive function call will eventually return back the answer for these determinants. So determinant B would effectively call again the function as plus dot dot dot, and then this would get the B11 term times the determinant of the submatrix C1, which this now in our particular example would be a 2 by 2, which the routine should automatically answer back. So this actual value is calculated, returns back up to this as a number, which gets multiplied by A1, added together with the other terms in this, and that falls back. So by definition, matrix determinants of matrices is a very recursive process. So you now see how to do the determinant of a 2 by 2 matrix, the determinant of an n by n by the method of expansion of cofactors based off of either a row or a column. I think it's easier just to deal with a row because that's what I demonstrated. You should now be able to develop an algorithm for this process.